All right, hello everyone. Today we're going to be going over section 6.1, which is on greatest common factors or factor by grouping. So we have four objectives. We want to find the greatest common factor of a list of numbers. We want to find the greatest common factor of a list of variable terms. We want to factor out the greatest common factor, and then we're also going to factor by grouping. So just as a reminder, recall to factor a number means to write it as, oh, I see I wrote to write twice, to write it as a product of two or more numbers. So for example, 12 is equal to 6 times 2, where our factors are 6 and 2. But when we write out or we express 12 as, if we express 12 as 6 times 2, that's called factoring. We took our product and we expressed it in its factors. So objective 1, we want to find the greatest common factor of a list of numbers. So an integer that is a factor of 2 or more integers is a common factor of those two integers. The greatest common factor, or the GCF is what we're going to call it a lot, of a list of integers is the largest common factor of those integers. So for example, if we have something like 16, 48, and 52, this is going to have a greatest common factor of 4. They also have a common factor of 2, but its greatest common factor is going to be 4, since we see that 2 times 2 is actually contained in each one of these integers. So when finding the greatest common factor, use each prime the least number of times it appears in all factored forms. So starting with example 1, if we want to find the greatest common factor for the list of numbers, we have 18, 30, and 42. Now it's always most helpful to express all of our integers in their prime factorization form first. So starting with our first integer, number 18, we have 18 and we want to express this in prime factorization. So 18 is equal to 2 times 9, where 9 can be expressed as 3 times 3. So the prime factorization of 18 is 2 times 3 times 3. Now moving on to 30. We can express 30 as 2 times 15, where 15 can be expressed as 3 times 5. So the prime factorization of 30 is going to be 2 times 3 times 5. And lastly, we have 42. So 42, we can separate into 2 times 21. And 21 can be expanded into 3 times 7. So we have the prime factorization of each one of these numbers. And the thing that we want to notice in this case is that there is a 2 in each one of our numbers. So 2 is a common factor, but we also have 3. And 3 is found in each one of these prime factorizations as well. So what we need to do is we actually are going to multiply 2 times 3 to get that 2 times 3 is our greatest common factor. So in this case, 2 times 3 is the least number of times each prime number appears in all factored forms, is 2 times 3, which is equal to 6. So our greatest common factor is going to be 6. And if we think about it, this is our greatest common factor, so it's going to be the number with the most value that is still a factor of each one of these numbers as well. So all right, on to objective 2. We want to find the greatest common factor of a list of variable terms now. So instead of having numbers or integers, we're now going to have variables and variable terms. So the terms x to the power of 4, x to the power of 5, x to the power of 6, and x to the power of 7 have x to the power of 4 as the greatest common factor, since it's the least exponent on the variable x. So we can express x to the power of 5 as x to the power of 4 times x. We could express x to the power of 6 as x to the power of 4 times x to the power of 2. And we can express x to the power of 7 as x to the power of 4 times x to the power of 3. So we see we contain x to the power of 4 in each one of our variable terms. So x to the power of 4 would be the greatest common factor. So finding the greatest common factor, step 1, you want to factor. So you're just going to write each number in its prime factored form. Then you want to list common factors. So list each prime number or each variable that is a factor of each term in the list. If a prime does not appear in one of those prime factored forms, it cannot appear in the greatest common factor. Step 3, choose least exponents. So use exponents in the common prime factors, the least exponents from the prime factored forms. And step 4, multiply the primes from step 3. If there are no primes left of step 3, the greatest common factor is 1. So using this, this idea, we want to apply this now to variables and integers. So example 2, we want to find the greatest common factor from the list of integers and variables. So we have 15x squared y, 27xy cubed, and 39x to the power of 4 times y to the power of 2. So we want to express each one of these terms as the prime factorizations. So 15x squared y, 15 can be expressed as 3 times 5. X squared can be expressed as x times x times y. So there's our factorization of 15x squared y. Now for 27xy cubed, 27 has a prime factorization of 3 times 9, which 9 could be expressed as 3 times 3 as well. Then we have times x, times y, times y, times y. And lastly, 39, x to the power of 4, y to the power of 2. 39 is the prime factorization of 3 times 13 times x times x times x times x times y times y. So we want to identify the number of terms that show up in each one of our prime factorizations. So starting with integers, we see that 3 appears once in each one, or at least once in each one of our prime factorizations. So 3 is part of our greatest common factor. Now let's move on to x. So there's at least one x in each one of our terms. Then on to y, we see that there's also at least one y in each one of our variable terms again. So combining each one of these terms, we get 3 times x times y, which is just equal to 3xy. So our greatest common factor is 3xy. So all right, on to objective 3. For objective 3, we want to factor out the greatest common factor. So factoring a polynomial is the process of writing the polynomial sum in factored form as a product. So for example, something like 3m plus 12 is going to be equal to 3 times m plus 3 times 4, which then you see that there's a 3 in both terms, so you can pull out the 3 and say 3 times m plus 4. So the factored form of 3m plus 12 is going to be 3 times m plus 4, and this process is called factoring out the greatest common factor. So a word of caution, the polynomial 3m plus 12 is not in factored form when written as 3 times m plus 3 times 4. This isn't factored form since we see that 3 is still written as a multiplication of each term. Your 3 needs to be taken out of the equation, multiplied by whatever was left over in those cases. So it's almost like you're doing a backwards distributive property. So it's already been distributed and now you're moving backwards. So the terms are factored, but the polynomial is not. The factored form of 3m plus 12 is the product 3 times m plus 4. Since we see the factors are going to be 3 and m plus 4. So for example 3, we want to factor out the greatest common factor from the expression. So we have 15a squared minus 25a cubed plus 40a. So let's go ahead and write out our prime factorization of each term, but in this case we are just going to expand it in its own equation. So for 15a squared, we can write this as 3 times 5 times a times a. So that's 15a squared. Then we have minus 25's prime factorization is just 5 times 5 times a times a times a. Then lastly, 40 times a, 40's prime factorization is going to be 2 times 20, which is 5 times 4, which is 5 times 2 times 2 times a. So now we want to identify what factors appear in each one of our factorizations. So we see there's at least one 5 in each factorization and one a. So 5 times a, which is just 5a, is the greatest common factor. So we've identified our greatest common factor, and now we want to factor it out. So we want to express 5a times 15, or a squared times, 15a squared. We want to express this as a factor of 5a and something else. So 15a squared divided by 5a is going to be 3a. Or we can just identify whatever was left over in this case, which was 3a. Minus 5a times 5a times a, which is going to be 5a squared. And then lastly, plus 5a times 2 times 2 times 2, which 2 times 2 times 2 is just going to be 8. So we have 5a times 8. So now we have 5a in each term, and now we can factor it out. So we can write 5a times whatever's left over inside of our parentheses. So we'll have 5a times 3a minus 5a squared plus 8. And that's how we would factor out a greatest common factor from an expression. And our last objective, objective 4, we want to factor by grouping. So when a polynomial has 4 terms, common factors can sometimes be used to factor by grouping. So factoring a polynomial with 4 terms by grouping, step 1, we want to group our terms. So we're going to collect the terms into 2 groups so that each group has a common factor. Step 2, we want to factor within the groups. So we'll factor out the greatest common factor from each group. So we'll have 2 separate greatest common factors. Step 3, if possible, factor the entire polynomial. So factor out a common binomial factor from the results of step 2. Step 4, if necessary, rearrange terms. So if step 2 does not result in a common binomial factor, try a different grouping. And you always want to check the factored form by multiplying. So we want to check and see if it's correct in the end by multiplying it by our original. So we want to factor the expression by grouping. We have 2xy plus 12 minus 3y minus 8x. So you have to think of a few different ways to group this. If we just go ahead and say, oh, okay, well, let's group it this way. We can see that while 2xy plus 12 has a greatest common factor, 3y minus 8x doesn't. So we don't want to group it this way. But we see that 2xy minus 3y is going to have a common factor of y, and 12 minus 8x is going to have a common factor of 4. So let's write it this way. So let's write 2xy minus 3y plus 12 minus 8x. We're going to group it like this. And this would be our step 1. So let's write step 1. We want to find a way, and when we group these, we want one group to have a variable as a greatest common factor. We want the other group to try and have a like a constant, but it can also have a variable. You just want to make sure that at least one of them has a variable instead of having two constant terms as the greatest common factor. So we have 2xy minus 3y plus 12 minus 8x. Now we're going to factor within our groups. So step 2. If we do prime factorizations, we're just going to get 2 times x times y minus 3 times y. So in this case, it's fairly clear that y is our common factor. Now for our second expression here, we have 12 minus 8x. Prime factorization of 12 is going to be 3 times 2 times 2 minus 8 times x, which is 2 times 2 times 2 times x. Where in this case, we see 2 times 2 appear in both expressions. So in this case, we have a greatest common factor of y, and over here we have a greatest common factor of 2 times 2, which is 4. And now for step 3, we want to factor the entire polynomial. So once we've identified, another part of step 2 here actually, is that once we've identified our greatest common factor, we're going to factor them out. So now we're going to have y times 2x minus 3 plus 4 times 3 minus 2x. So this is our new expression. And now what we're going to see here is that for step 3, we want to factor the entire polynomial if possible. So our goal is that we want to factor out a common binomial factor from the results of step 2. If we want to factor out a binomial, it's actually going to be fairly difficult because what we have is y times 2x minus 3 plus 4 times 3 minus 2x. Seemingly, we have different expressions in our parentheses, and then we have these coefficients. But what we can do is 2x minus 3 and 3x minus 2x, 3 minus 2x, are fairly similar except for the fact that they're a difference of -1. So instead, we're going to say -4. We're going to factor out a -1 out of our equation of 3 minus 2x. And when we do, this is going to give us, and we can rearrange this a bit, this will give us 2x minus 3. So now we see that these expressions are the same. So if you ever work this out and there's a case where they are extremely similar but not exactly the same, try and see if you can factor out a negative in that equation and see if you can make it the same. So in this case, they were the same equations if we pulled out a -4 instead of a +4. But now we have that 2x minus 3 is the same, and now we're multiplying 2x minus 3 by y plus -4. So now our greatest common factor is 2x minus 3. This is our new greatest common factor for our polynomial. And so if we want to factor out our common binomial factor from the results of step 2, this means that we're factoring out 2x minus 3. So we can pull out 2x minus 3, and when we do, what we're left with is y plus -4, which is the same thing as saying y minus 4. And this would be the factorization of our polynomial. We don't need to do step 4 because step 4 is just saying, if necessary, rearrange your terms, which we don't need to. So we're saying that this is the factorization of our polynomial. So factorization of polynomial. And now we just want to check and make sure this is correct. So to check and make sure these are correct, we're just going to FOIL. So 2x minus 3 times y minus 4. When we FOIL this expression, we multiply our first terms, so we have 2x times y, multiply our outside or our outer terms, so plus 2x times -4. Then our inner terms, -3 times y, and lastly our outer terms, -3 times -4. And simplifying this will give us 2xy minus 8x minus 3y plus 12, where our original equation was 2xy plus 12 minus 3y minus 8x, which we can rearrange this to say 2xy minus 3y, too far. Sorry, it was plus 12 minus 3y. Plus 12 minus 3y minus 8x. These expressions are the same. We can rearrange them. So this is correct. So there we have it. That concludes section 6.1. So I'll see you all again in section 6.2.